All right, so the speed limit of the universe, the speed of light. Um, it's a question we get a lot, and you've sent in a ton of stuff for this deep dive. Articles, excerpt, even some in another language. Wow.
Yeah, it really is one of those questions that just captures the imagination, isn't it? And to really get it, we need to talk about Einstein, his theory of relativity.
Okay, so relative, I think most people, when they think about time and space, they think about it as like, well, it's just kind of always there. You know what I mean? It's just, it's fixed.
Yeah,
Yeah.
I mean, that's how we experience it day to day,
Yeah,
right?
yeah.
But Einstein, he really kind of shattered those assumptions. What he showed was that time and space, they're actually intertwined. They're not separate things. And together, they form kind of this fabric, this structure, and we call it space-time.
Space-time.
Yeah, and the thing is, this fabric, it's not static. It's not just sitting there. It can warp, it can stretch, it can bend.
Okay, I'm trying to visualize this.
Think of a trampoline.
Okay, trampoline.
You put a bowling ball on that trampoline, what happens?
It sinks, it makes a diff.
Exactly, exactly. So massive objects in the universe, things like stars, planets, they do the same thing to space-time.
They make a dip in space-time.
They create these curves, these distortions. So massive objects warp the fabric of space-time.
Okay, all right, so I'm starting to see where this is going.
Yeah, so now comes the really mind-bending part. The speed of light, it's always constant. It doesn't matter what. So imagine a beam of light traveling through this warped space-time. It's always going to travel at that same speed, even if it's passing by, a massive object that's creating a curve.
So even if I'm like in a spaceship and I don't know, chasing a beam of light at half the speed of light, it's still moving away from me at the speed of light.
Exactly. It doesn't matter how fast you're going, you'll never catch up. The speed of light is constant relative to any observer.
Whoa, okay, that is wild.
It seems counterintuitive, I know, but that's relativity for you. It's one of these really fundamental constants of the universe. It's the ultimate speed limit.
But why is it the limit? Why can't we just, I don't know, push past it?
Well, think about it this way. As an object speeds up, its mass increases. To keep accelerating, you need more and more energy.
So the faster you go, the harder it gets to go faster. Like pushing a shopping cart that's getting heavier and heavier.
Yeah, it's kind of like that.
Okay.
Now imagine trying to reach the speed of light. What happens? According to Einstein's equations, you would need an infinite amount of energy.
Infinite.
And we don't have an infinite supply of energy. It's just not possible. So reaching the speed of light is impossible for anything with mass.
So the universe is basically set up to prevent us from reaching the speed of light. The energy requirements just, they become impossible.
Yeah, you could say that. It's like a built-in safety feature, and it all boils down to this really profound connection between mass, energy, space, and time.
It's fascinating, really. So while, all the sci-fi stuff of zipping around faster than light, maybe that'll always stay in the movie.
For now, at least.
Yeah, but even just understanding why that speed limit exists, I don't know, it just helps you kind of grasp this really fundamental part of how the universe works,
Oh, absolutely. And you know what? This is really just scratching the surface. Einstein's theory of relativity, it predicts all these other crazy effects that happen when you approach the speed of light.
Oh, okay. Like what? Give me a teaser here.
Well, one of the most interesting is something called time dilation. Time itself actually slows down for objects that are moving close to the speed of light.
Wait. Are you saying time travel is possible?
Time travel to the future is definitely theoretically possible. The faster you move, the slower time passes for you compared to someone standing still.
So if I hopped in a spaceship and I was, I don't know, blasting off near the speed of light, time would actually slow down for me compared to everyone back on Earth.
Yeah. Of course, we'd need a spaceship that could actually travel that fast, which, again, brings us back to that energy problem. But the idea of time dilation, it's been experimentally proven. Atomic clocks, they've been flown on airplanes, and they tick a little bit slower than clocks on the ground.
Really?
It's true.
Wow. So time, it's not this fixed thing for everyone. It's relative.
Exactly.
Okay, my brain is starting to hurt a little bit. But this is really cool.
It's just the tip of the iceberg, really. There's so much more to explore with Einstein's relativity, so are you ready for some more mind-bending stuff?
Oh, absolutely.
Yeah.
You were talking about time dilation. What other weird things happen near the speed of light?
Okay, well, there's something called length contraction.
Length contraction.
Yeah. And basically, as an object gets close to the speed of light, it actually appears shorter in the direction it's moving.
So like if a spaceship was flying by us really, really fast, like near the speed of light, it would look squished.
Exactly. And it's not just an optical illusion or something. The object actually physically shrinks. From the perspective of someone who's standing still anywhere.
So to someone on that spaceship, it looks normal.
To them, everything seems fine. But to us watching, it's shorter.
Wow. Okay, time slows down. Things get shorter. Is there anything else that gets, like, distorted at these crazy speeds?
Well, mass is affected too. As you get closer and closer to the speed of light, your mass increases.
Ah, so you get heavier.
You got it. And that's actually another reason why hitting the speed of light is impossible. You'd become infinitely massive, and it would take an infinite amount of energy to speed you up anymore.
So it's like the universe has these rules in place to keep us from breaking that speed limit.
Yeah, that's a good way to think about it.
It's amazing, really. All these things, time, space, mass, energy, they're all connected.
It really shows how everything in the universe is intertwined. It's mind-blowing. And it all comes back to that idea from Einstein, that the speed of light is constant for everyone, no matter what.
This has been an incredible deep dive so far. But I got to ask, we've been talking about special relativity, right?
Right.
But earlier you said that Einstein had two theories of relativity. What are the other one?
Ah, yes. General relativity. That's where things get even wilder.
Okay, I'm intrigued. What's general relativity all about?
Well, special relativity, that's about constant speeds, like our spaceship example. General relativity, it deals with acceleration and gravity.
So it's like special relativity but supercharged.
I guess you could say that.
Right.
It takes those ideas from special relativity and adds gravity to the mix. And Einstein, he had a completely new way of thinking about gravity. He realized that gravity isn't a force, but a curvature of space-time.
Hold on, wait, gravity isn't a force? I thought that was like a basic law of physics.
I know, right? That's how we usually think about it. But Einstein, he was a genius. He saw things differently. He said massive objects, they actually warp space-time, and that warping is what we experience as gravity.
I think I remember you talking about that earlier with the trampoline example, right?
Exactly. The bowling ball on the trampoline. Just like that, a massive object like the sun, it makes a dent in space-time. And objects like the Earth were basically just falling along those curves created by the sun.
Whoa. So it's not that the Earth is pulling on me with gravity, it's that I'm following the curve of space-time that the Earth creates.
Yeah, you got it. General relativity tells us that gravity isn't a force acting over a distance. It's actually a property of space-time itself.
Wow, okay, this is blowing my mind. So what else does this warping of space-time explain? What are some other things that happen because of it?
Well, one of the craziest things is black holes. These are regions of space-time where gravity is so strong that nothing, not even light, can escape.
Black holes, those like cosmic vacuum cleaners that just suck everything up. I've always been fascinated by those.
They really are fascinating. They form when massive stars collapse at the end of their lives. And their gravity becomes so intense, so strong, that it warps space-time to an extreme. Like, imagine that bowling ball on the trampoline making a dip so deep that nothing could ever climb out.
So even if you could travel at the speed of light, you couldn't escape a black hole.
Nope, you're trapped. Once you cross that point of no return, the event horizon, you're pulled towards the singularity at the center. And at the singularity, all the laws of physics as we know them, they just break down.
Black holes, they sound terrifying, but also incredible. Like there's these extreme labs where we can study the limits of gravity and space-time.
Yeah, exactly. And they're one of the many reasons why general relativity is considered one of the greatest scientific achievements ever.
I'm starting to understand how general relativity works. But why is it so important? Does it have any use outside of explaining black holes?
It's crucial for understanding the universe on a grand scale. General relativity helps us explain how planets orbit stars, how light bends around massive objects, even the expansion of the universe itself.
So general relativity isn't just some cool theory. It has real applications in, like astronomy and cosmology.
Absolutely. Like our whole understanding of how the universe evolved from the Big Bang to today, it's based on general relativity.
Okay, so this is pretty important stuff.
It is. And, even everyday things like GPS, they wouldn't work without taking into account the effects of time dilation predicted by general relativity.
Wait, my GPS uses Einstein's theory? How does that work?
Well, those GPS satellites, they're orbiting Earth really fast, right? And because of time dilation, their clocks run a little slower than clocks here on the ground. If we didn't correct for that difference, our GPS would be way off.
So Einstein's theories aren't just for physicists, they affect our everyday lives.
That's right.
It's amazing to think about these ideas, from over a century ago, and how they're still shaping our understanding of the universe and our place in it.
It's incredible, isn't it? It really shows the power of human curiosity and the lasting legacy of Einstein.
All right, I need a minute to process all of this. We've talked about special relativity, general relativity, black holes, even GPS satellites. It's a lot to take in. Ooh, I think I'm finally starting to wrap my head around all this. It's amazing how these concepts, they sound so abstract and complicated, but they actually have real-world effects, like with GPS. Going through all this material for our deep dive, one thing that really caught my eye was gravitational waves. That sounds like something straight out of, like, Star Trek or something.
Yeah, it does sound pretty sci-fi. But gravitational waves, they're a real thing. One of the most mind-blowing predictions to come out of Einstein's general relativity.
Okay, so break it down for me. What exactly are these gravitational waves?
All right, picture this. You've got two incredibly massive objects, like, say, black holes, orbiting each other. And as they spiral closer and closer together, their intense gravity, it actually warps the fabric of space-time, and it creates ripples, and these ripples spread outwards, traveling at the speed of light. Those ripples, those are gravitational waves.
So instead of waves like in water, we're talking about waves in space-time itself.
Exactly. It's pretty incredible when you think about it. And just like waves in the ocean, gravitational waves, they carry energy and information.
So by studying them, we can learn about what's happening out there in the universe.
Exactly. We can learn about some of the most extreme events in the cosmos. Things like black hole collisions, exploding stars, maybe even get glimpses of the Big Bang itself.
Wow. Okay, so how do we actually detect these waves? They must be, like, super faint by the time they reach us.
Yeah. Detecting them is incredibly difficult. Gravitational waves, they're unbelievably weak, and they cause these tiny, tiny changes in space-time. But scientists, they've built these amazing instruments called interferometers to try to pick up on those changes.
Okay, how do those work?
They use lasers to measure extremely small changes in distance. So they basically split a laser beam and send it down two long tunnels, like set at a right angle. The beams bounce off mirrors and come back to the starting point. And if a gravitational wave passes through, it stretches and squishes space-time a tiny bit. And that causes a tiny change in the distance traveled by one laser beam compared to the other.
So we're talking about, like, measuring changes that are smaller than an atom.
Pretty much. It's an amazing feat of engineering and a real testament to human ingenuity. And you know what? Back in 2015, the LIGO experiment, they actually did it. They made history. They directly detected gravitational waves for the very first time.
Wow, what did they find? What were those first gravitational waves?
Those waves, they came from two black holes colliding over 1 billion light years away. Imagine that, an event so powerful, so cataclysmic that we could detect its echoes here on Earth over 1 billion years later.
That's mind-blowing. We can basically listen in on these cosmic events happening across these incredible distances. It's like having a whole new sense, a new way of experiencing the universe.
You got it. It's a completely new way to study the cosmos, to explore things that were invisible to us before. It's a really exciting time to be an astronomer.
It really is. We started this deep dive just wondering why the speed of light is a limit. And we've gone on this amazing journey. We've explored Einstein's relativity, the idea that space-time itself can be warped. We even talked about black holes and gravitational waves. This has been an incredible deep dive.
It has. It just shows you even the simplest questions can lead to the most profound discoveries. The universe is full of surprises.
And the journey's not over. There's still so much out there to explore, so many mysteries left to unravel. So to everyone listening, keep asking those big questions, keep exploring, keep looking up at the stars. Who knows what incredible things we'll discover next?